Hi everybody, let's get a little bit more in-depth about vectors today. We're going to start off by talking about unit vectors. These are a different way to specify vectors that can be really useful, especially when you're going to be multiplying vectors, which we're going to have to do. So let me explain what they are. First of all, there are three unit vectors, and the idea is a unit vector has a magnitude of 1, that's why it's called a unit vector, and a direction in one of the principal axes. So for example, I, with a little hat on top of it, I'll draw this again. So it's an I with a little party hat, okay? That has a magnitude of 1, and it points in the positive x direction. And I'm showing it over here. That's, oh, let me turn this a little bit to the left. Oh, it's going to run off screen. Okay, this is the x-axis here that I'll just put this back so we can get everything on the screen at the same time. Okay, so the I unit vector points in the x direction. Okay, the J unit vector, all right, it's a lowercase j with a little party hat, all right, that has a magnitude of 1 and it points in the y direction. So if this is my x-axis, this is my y-axis, the J unit vector points in the y direction. And then the K unit vector, here we go, it's a K, again with a little party hat. All right, it has a magnitude of 1 and it points in the positive, oops, that's a mistake, points in the positive z direction. All right, and so in my axes here, x is to the right, y is up, and z comes straight out of the board, out of this sheet of paper. There's no way for me to actually do that nicely, so I've drawn this axis, and this z is pointing out, or up, away from this plane, okay? I, J, and K are all at right angles. I goes with X, J goes with Y, K goes with Z. All right, so now that we know that, let's talk about a little bit more about these. And I'll show you an example of unit vectors and kind of how we work them. All right, so first of all, we can specify a vector using the old-fashioned way. So displacement equals 10 at 36.9 degrees. So here's my 0 axis, 39.6 degrees up. Here's my vector, my displacement of 10. There it is. That's what it looks like. Here's how we write it, old-fashioned way. With unit vectors, what we would write is displacement equals 8 in the I plus 6 in the J. Well, here's my 8 in the I direction, basically 8 in the X direction. Here's my 6 in the J direction, 6 in the Y direction. And if you look from here, start to end, that is exactly the same as the start to the end in our previous example. These are two equivalent vectors. And here's what's going on with this 8. Basically, this is saying delta x equals, all right, the magnitude, so it's going to be 10 times cosine of the angle, 36.9, okay, and this is in the I direction, plus 10 times the sine, 36.9, and that's in the J direction. And of course, 10 times cosine, 36.9, that gives you 8. All right, so this whole chunk right here gives us the 8. I shouldn't have drawn that. And this whole chunk right here, that gives us the 6. And if you don't believe me, just try it out, okay? All right. So once we have unit vectors, they're really easy to work with because, well, first of all, let's go to addition. Okay, so if we're going to add two vectors, and they're specified with this old-fashioned way, we got to find the components, add up the components, and then do like an tangent to find the angle, and Pythagorean theorem to find, inverse tangent to find the angle, Pythagorean theorem to find the magnitude. We don't have to worry about that if you're talking unit vectors. So here I got two unit vectors. Displacement 1, 8i plus 6j. So that's 8 in the x direction, 6 in the y direction. Okay. Displacement 2, we got minus 12 in the I direction, 4 in the J direction. Remember, this is a perfectly valid way of specifying a vector now. We're just using what's called unit vector notation. So when I add those up, displacement 1 and displacement 2, here's what you do. You just take the parts that are in the x direction, right here and right here, and you add them up. 8 minus 12. And what? Guess what? It's still in the x direction, so we're going to call that I. So what's that end up being? Minus 4 in the I direction, which is the x direction. Okay? All right. So then you do the same for the y. So you add up the two things from the y, 6 and 4, 6 and 4, and that's going to be in the j direction, which means the y direction. Okay? All right. So your final answer, minus 4i plus 10j. And this means minus 4 in the x direction, and then plus 10 in the y direction. So we're talking about a vector that looks like this. Right here, that big thing that I drew at the end. That's this. Okay? So that's adding with unit vectors. All right. So now let's talk about just multiplying vectors in general. Okay, so let's bring this down here. Okay, when you multiply vectors, all right, move this over here. When you multiply vectors, okay, so I'm going to multiply a vector and a scalar. And here's what happens. Oh, I don't like what's going on with my screen. Okay, when I multiply a vector and a scalar, the scalar, remember, scalar is just an amount. The scalar just tends to, ready for this, scale up or down the vector. That's why it's called a scalar, kids. Okay, so here's what you do. So here's a unit vector. I got a vector A, not necessarily acceleration, just some vector A. And it's 3i plus 2j plus 4k. All right, and I want to multiply it by a scalar. I want to multiply it by 3. So what does 3a, that vector A, equal? Well, 3a equals 3 times 3i. Remember, this is 3i. I'm just going to multiply it by 3. I'm just going to make it bigger. Plus 3 times 2j. I started with 2j. I'm just multiplying it by 3. Plus 3, remember, that's my scale. That's what I'm scaling it up by, times 4j. There's the 4j. Okay? All right, so you got 9i plus 6j plus 12k. Multiplying a vector and a scalar is as easy as that. Okay, so now let's do the next one. Okay, if you multiply a vector, oh, I got to bring this down, sorry. If you multiply a vector and another vector, things get kind of crazy, okay? Sometimes when you multiply a vector and another vector, you get a scalar back. This is called taking or finding the scalar product or the dot product, all right? Other times when you multiply two vectors, you get a vector back, and that's called doing the vector product or doing a cross product. All right, so now let me just show you a couple instances. And what you end up doing all depends upon what you're looking for. So here we go. I got a for example. Oh, that barely fits. Hold on. I'm going to make this a little bit so I can see a little bit more. Ooh, I just made myself smaller so I can make this a little bit bigger. All right, so here we go. Example number 1. All right, and there's a lot of words here. I'm just going to talk about it. All right, we got this thing called work. Work equals force times how far. Force is a vector, how far is a vector. When I multiply these two things together, I'm doing a dot product. Hey, guess what? I got a dot there. Or a scalar product. I'm going to get back the amount of work, and work is a scalar. There is no direction associated with work. Okay? Now, I'm going to multiply a force and a displacement again, and watch what happens. So this time down here, for my other example, we've got this thing called torque. Think of a torque as a rotational force. And here's how it works. So let's say I've got some object, I don't know, a crazy looking object, and here's the pivot point for that object, and I'm going to apply a force right here, and that force is going to be at some distance r, some radius r, away from the pivot point. So down here's the pivot point. All right, and eventually we'll get to how you do forces, how you do torques. I'm not trying to teach you how to do torques. I'm just showing you about multiplying vectors, okay? So in this case, we're going to do the same thing. We're going to multiply a displacement, that's the r, and a force again, and we're going to get torque. So torque is actually a Greek letter tau, And torque equals R, that's the displacement, times, and this time I use a little time signal, like a cross. Oh, because it can be called a vector product or a cross product, okay? So R cross force, okay? And when you do these two, you get a direction. Torque has a direction. Torque is a vector. So when doing dot product, and remember, in both these cases, there was a force and a displacement. It just, what you did depended upon what you were trying to figure out. All right, so here, when you do a dot product, you get a scalar. When you do a cross product, you get a vector. Okay, and we're going to talk a little bit more later about, I think, about the actual direction of the torque. All right, so here we go. Now let's talk about dot products. Okay, so we're going to talk about dot products now. That's where you multiply two vectors and you get back a scalar. We'll talk about cross products or vector products later on, where you multiply two vectors and you get a vector. Okay, so here we go. There are two different ways, get those fingers in there, that you can multiply dot products. All right, and it kind of depends upon what information you have and what you're looking for. Okay, so there's two ways to do it. So if you know the angle between your two vectors, or, this is the important one, or if you're trying to figure out the angle between your two vectors, you're going to do a dot product kind of the old-fashioned way. Okay, I got A dot B, so I'm going to multiply these two vectors, the A and B vector, and we're going to get a scalar back. And the scalar ends up just being A times B times the cosine of the angle between them, where A right here is just the magnitude. It is the size of this vector. B is just the size of that vector. Okay? All right, this works particularly well if you've got things like, oh, here's A, and oh, here's B, and there's some known angle between them. Okay? And it's really easy to do a dot product on those. All right, now we can do dot products with unit vectors. So here we go. This one gets kind of nuts. All right, A dot B equals, all right, here we go. Here's my first vector. This is my A vector. And what it means is the x component of the A vector in the I direction, which is the x direction. The y component of, hold on a second. Man, this looks fuzzy. All right. The y component of the A vector in the j direction, which is the y direction, and the z component of the A vector, of course, in the k direction, which corresponds to the z. All right, so this represents my A vector, and I'm going to dot it with, all right, this represents my b vector. And I'm going to now do the actual math and think of a giant foil. I'm going to take this term, and I'm going to multiply it by this one, and I'm going to add that to this term multiplied by this, and I'm going to add to this term multiplied by this. That's this line here. So AX, all right, dot the BXI. So AXI dot BXI. And the second term is AXI dot BYJ. AXI dot BYJ. All right, the third term, I'm still with the AX in the I direction, and I'm going to dot that with BZ in the K direction. Okay, so that just handled the X direction of my A vector, but I still have a Y direction and a Z direction to go through. So here we go. Here's the next line. AY in the J direction times BX in the I. AY in the direction, in the J direction, BY in the J. AY in the J, BZ in the K. All right, so my third term is when I'm dealing with this one, and they all start with AZ, okay? So if you look at this, the way this kind of lays out, all right, the first thing being dotted together is always the same on each line. AX, 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 all right, AY, 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 AZ, AZ, AZ. The second thing goes along with the columns, BX, BX, BX. BY in the J, BY in the J, BY in the J. Okay, got the idea? All right, so now what does this actually, how do you actually deal with this? So let's just think about this idea right here. So remember from way up here that A dot B equals AB cosine theta. And if you know that cosine of 90 degrees is 0, here's what's going to go on. So any scalar products where the unit vectors are at right angles, they just drop away. So anytime I have two unit vectors that are at right angles, they'll just drop away. So for example, this first one, AX in the I, BX in the I. Are these two directions, I and I, at right angles or not? Ooh, I don't think they're at right angles. This does not drop away. But here, AX in the I dot BY in the J. I, that's in the X direction. J, that's in the Y direction. Those are at right angles. This is going to drop away. All right, AX in the I dot BZ in the K. Okay, the I here and the K here at right angles, they're going to drop away. All right, so when you do this, here's what you end up getting. Okay, this first chunk stays because they're in the same direction. Okay, the I and the J are in 0 degrees. Cosine 0 is 1. It stays. Okay, this one stays. This one stays. The other ones all go away because the two directions that you're dotting together are at right angles with each other. So once I have this, now I'm just going to kind of draw it, getting rid of all the 0 parts. So I got AX in the I dot BX in the I, AY in the J dot BY in the J, AZ in the K dot BZ in the K. All right, so that's what I got. Now let's do another remember. Let us remember that, of course, we're back to our kind of definition of cosine. A dot B equals AB cosine theta. And that cosine 0 equals 1, I believe I just said that a second ago. So if cosine 0 equals 1, when I take I hat, and I'm going to dot that with I hat, all right, the angle between those two vectors is 0. So that means the cosine theta part becomes a 1. So it ends up just being the A part multiplied by the B part, because the two directions are going to give rise to a 1 coming out of this cosine. So in the end, here's what you end up getting. Doing a dot product using unit vectors, and this is in 3 dimensions, really easy. You just add up the X components of your two different vectors, add up the Y components of your two different vectors, multiply the X components of your two vectors, add to that your Y components multiplied together, add to that your Z components multiplied together. Now, if this is just a planar problem, just the X and the Y, there is no Z to it in the B at all, then guess what? You've got no components in the Z. That just goes away. All right, so it becomes even simpler. It's just, hey, the two X's, the two X components multiplied, add that to the two Y components multiplied. Okay, but if you do have a three-dimensional problem, you got to include the Z term. All right, so that is how you do a scalar product or a dot product, shown both with the old-fashioned way of kind of defining it and then unit vectors. All right, moving on. Okay, now bring this down. Now let's talk about the vector product or the cross product. This is where you multiply two vectors and you get a vector. All right, here's where you would use this. Okay, I'm going to show you the old-fashioned way right here. Okay, the old-fashioned way. All right, you'd use, if you know the angle between the two vectors, all right, you'd use the old-fashioned way. All right, if you have unit vectors, you're going to do what I'm going to show you in just a second. So here comes the old-fashioned way. And hold on, I think there's like some smudge on my screen. I'm going to see if I can't make this a little clearer. It's just a slight bit out of focus and it's driving me bananas, bananas, bananas. All right. Maybe that did nothing at all. It did nothing at all. Okay. Anyway, moving on. So here's how you do kind of the basic cross product way. Okay, so let's say I've got a vector A and I've got a vector B, and I want to do a cross product between them. And of course, we have an angle between them called theta. Okay, what you get is A times B times sine of the angle. That's how you do the cross product. All right? So A is, again, just the magnitude of A. B is just the magnitude of B, just the size of it. And then sine of angle. Okay, so now the angle is a little bit more than just the angle between the two vectors we had last time. This one definitely is the angle from your first vector, A, to your second vector, B. The direction ends up being important. It's from A to B. All right. So we could draw this a little bit differently. We could go, all right, so here's vector A, and here's vector B. And then the angle from A to B has nothing to do with this. Oops, I didn't do that right. The angle from A to B is continue A, go from the direction of A to B. That's the angle right there. Okay, so this is all great, except for we know we have to get a vector out of it. And this just told me how to get the magnitude part. All right. So the vector, what you do is, to get the direction is, you're going to do something called the right-hand rule. But before we even get to the right-hand rule, I want to let you know that the direction of this cross product, A cross B, is always going to be at a right angle to the plane that contains A and B. So in this case, A and B are both on my sheet of paper. So the direction of this vector product is either going to be pointing up away from the sheet of paper, because that's at a right angle to this plane, or it's pointing down into the sheet of paper. That's the direction. All right? Now, the way you figure out whether it's pointing up or pointing down, you use this thing called the right-hand rule. And okay, so here's the right-hand rule. All right? Right-hand rule. First of all, you point your fingers in the direction of the first vector. All right, so here I'm going to take my fingers, and I know what's going to happen, so I'm just going to kind of do it. All right, so my fingers are going to point in the direction. Oh, look, there's my fingers. And you see how they're pointing in the direction of the A? All right, they're pointing in the direction of the A. All right, now I could point them in the direction of the A this way. I could point them in the direction of the A this way. There's lots of ways I can point them in the direction of A. You got to find the way that ends up working out nice. So here we go. Let's try this again. So here's my fingers pointing in the direction of A. All right. Then the second thing to say is bend your fingers towards the second vector, what I'm calling the B vector. All right. So if I have my hand oriented this way, my fingers naturally can bend towards that B vector. Notice, if you will, if my fingers were this way, it's not natural. Some people are like, oh, I can bend my fingers that way. So what? It's not natural. So you put my finger, I want natural bending. So I put my fingers this way, and they naturally want to bend towards B. Now, which way is your thumb pointing? And I'm looking for a hitchhiking thumb, not a karate chop thumb. Oh, no, hitchhiking thumb. Karate chop, no. Hitchhike, yes. All right, so here we go. Back to the right-hand rule. Put your fingers in the direction of A, bend them towards the second one. Fingers, the first one, bend towards the second one. Whichever way your thumb points, that is, of course, a hitchhiking thumb. Then that's the direction of the vector, okay, of the resulting vector. In this case, it is pointing up away from the sheet of paper because my thumb's pointing up, all right? Okay, so that's the right-hand rule. That's how you figure out these vectors, okay? One last thing. I cannot understate this. It is vitally important that you keep in mind direction. A cross B is not equal to B cross A. It just doesn't work. Okay? It's not, whatever this property is in regular multiplication doesn't work with vector multiplication. All right. So that's how you do a vector cross product if you've just got two vectors and an angle in between. Okay. By the way, you'd never want to use this method to find the angle. You'd go back and use a dot product if you needed to find the angle between two vectors. All right, moving on. Here we go. Now what we're going to do is we're going to add up, we're going to do a vector product with unit vectors. Okay. So here we go. A cross B equals, well, there's my A vector. Oh, look, there's the cross, and here's my B vector. All right. Okay, for the next step, think about doing a giant FOIL, just like we did before. All right, I explained it before, same exact explanation. Okay, so it's going to be A, X in the I direction, cross, bx in the I direction. Right there. Ax in the I cross bx in the I. Then ax in the I cross by in the j. Ax in the I cross by in the j. Then ax in the I cross bz in the k. Okay, so we go through that whole thing and we get these terms for our cross product. All right, next idea. Okay, so now let us remember that A cross B equals AB sine theta. All right. We got that from, I don't know where that sheet of paper went. Oh, got it from this sheet of paper. All right, right here. We're going to remember that idea. Okay, so remember that A cross B equals AB sine theta, and that sine of 0 is 0. So sine of 0, anytime these two vectors, these two directions are in the same direction, this term is going to go away. All right? Okay, my wife is here now. All right. Anyway, I got to keep recording. Okay. So the term's just going to go away. So here we go. Let's look at what happens, because 3 of them go away. All right, this first term has both our unit vectors are in the I direction. That goes away. Here, my unit vector is in the I, my other unit vector is in the j. That does not go away. Here, the unit vector is in the I, that's in the k. It does not go away. All right, so these 3 end up going away. The 2 that are both i's, the 2 that are both j's, and the 2 that are both k's go away. All right, so now let's rewrite that. Oh boy, it looks kind of weird. I've just taken wherever this was 0 and I put a 0 in. So now we're left with this. Okay. We're going to remember another thing, okay? All right, so real quick, I guess I could do this. There's no good way to cover this. Oh, there it goes. All right, now we have to figure out what's going on when I cross. And by the way, when I did this, I pulled out the AX and the BY. Those just got pulled out, and I just left the unit vector stuff together, okay? So now, here's what we're going to do. We just got to talk about what it means when I say I cross J. What direction is I cross J? And if we go back to the very beginning, and we had this. I vector cross J vector. Now remember, we learned how to do that now. I take your fingers and you point them in the direction of the first one. You bend them in the direction of the second one, and the way your thumb points, that's the direction of the third one. So I cross J is the K direction. Now there's a really cool way to remember this. It's this little circle here. All right. I call it what do I call it here? Unit vector circle. I don't know if that's a good name. But anyway, if you go in the direction of the arrows, you get positive results. So I cross J equals K. J cross K equals I. K cross I equals J. And it would work if you did your right-hand rule thing. All right. But anyway, now we're going to go the opposite direction. I cross K equals minus J. K cross J equals minus I. So if you're going in the direction of it, you get positive results. Go in the opposite direction, you get negative results. Okay, so we're going to use this to help us out. So right here, I got AX, BY, that's the magnitude, and here comes the direction part of it. I cross J. I cross J equals K, so that's got to be my K. All right, so if you see, I've just taken this whole thing and brought it down here, and instead of I cross J, it's equivalent to K. All right, what's our next one? I cross K. I cross K, I'm going in the backwards direction, that's got to be minus J. Okay. All right. So what's I'm getting interrupted. Okay. So here we go. I cross K is minus J. Here's our next one. I'm just going to pull this one down here. J cross I. J cross I, I'm going backwards around it, minus K. There's my minus K. All right, here's my next one. J cross K. J cross K is going to be I. Oh, look, that's an I. All right, and what do I got here? K cross I, that's going to be J. And K cross J, that's going to be minus I. All All right, so there they are, and I've actually done the cross product with the unit vectors. So now I can take this whole thing, this wonderful thing, and I can add up the common terms. So everything with an I, so that has an I, and where's the other one with that? This has an I. You can add those up. So AY, BZ, those are the components, times in the I direction, plus AZBY in the minus I direction. And I add up all the terms. Okay, so those are the I's. Where are the J's? Here's a J, and here's a J. So I got AZBX in the J, and then up here, AZBZ in the minus J. Okay, and then our K's, where's the K? All right, I'll circle the K's. All right, so there's the K's. So I got AXBY in the K, and AYBX in the minus K. All right, now just finish it up. I'm going to pull out the scalar parts along with a negative if there is one, and we end up with A cross B equals AYBZ minus AZBY, and that's all in the I direction. I'm going to add to that AZBX minus AXBZ, and that's in the J direction. Notice the direction is always perpendicular to the things that are inside the parenthesis. All right, last one. AXBY minus AYBX, that's in the K direction. If we start with something that is just in the XY plane, then guess what? If something's in the XY plane, I've got no B component. I'm sorry, I got no Z component here. I got no Z component here. This just goes away. This whole term goes away. If we're just in the XY plane, my resulting direction has to be perpendicular to that plane, which is going to be in the K direction or minus K direction. All right. So if you're just in the XY plane, these two go away, and A cross B ends up being just that. And where these are just the components. Okay. These are the things that start in front of our unit vectors. All right. Okay, we're almost there, but this is it. That's a huge result. Okay, that's very useful when you have three-dimensional vectors. All right, last chunk. You ready? By the way, this whole page, nobody likes doing that, and it makes this really difficult to memorize. I mean, you can memorize if you want to, but ugh. Okay, there's another way to do this very quickly if you know what you're doing, and it has to do with matrices. So here you go, matrices. Okay, so we're gonna add these unit, or we're gonna do a cross product on these vectors, and we're gonna solve it using a matrix. So here we go. Here's how I set up my matrix. In the I direction, I've got AX and BX. In the J direction, I got AY, BY. K direction, AZ, BZ. Okay. Now I'm gonna kind of bust this down into its three separate directions. Okay. So in the I direction, and you probably have learned this at some point, in the I direction, what you do, so for the I direction, what you do is you cover up I, and you look at just the remaining stuff. I've got AY, BY, AZ, BZ. Okay? Then for the next part, I'm going to cover up the J, because that's the direction I care about. Except when I cover it up, it looks all weird. Okay. Think about this idea, this kind of like rotational, this way of going around this how the unit vectors always one cross the second one equals the third one. That idea. Okay, I cross J equals K, J cross K equals I. All right, if you think about it that way, here's what happens. We can add on to this. I can say, all right, it's just there's a repetitive nature to the whole thing, so I'm going to say I AX, BX. So now when I cover up J, I can take the K and the I parts, all right, AZ, BZ, there's BZ, AX is right there, BX is right there. Because it's arbitrary that we started with the I vector first. I could have written this exact same thing starting with the J vector first, and this would have been my matrix. So when I cover up the J part, I'm left with just this. Okay, so that's how I get this one. K part, let's cover up the K, and we're back to just these. AX, BX, AX, BX, AY, BY. All right, now, how do you solve this little guy here? Well, the way you do that is, what you do is, in the I direction, it's going to be these two multiplied, subtract from those these two multiplied. All right, AYBZ, subtract from that AZBY, and that's in the I direction. AZBX minus AXBZ minus AXBZ, that's in the J direction. And the K ends up being AXBY minus these two, AYBX, and that's in the K direction. Okay, and guess what, everybody? It's really kind of cool because, let me fold this. What we got with matrix ends up being the exact same thing we got doing it the other way, exact same thing, and I personally think it's a whole lot quicker. All right, so that is your crazy crash course into unit vectors and how to add and subtract unit vectors. No, not add and subtract, multiply vectors, three-dimensional vectors. All right, until I see you again, adios, everyone.